Hello. This video is going to be about how I test for robustness for my algorithms. And this is made by a request by one of my subscribers. And I recently had posted a video about the target feed forward or command feed forward using only a proportional gain. And the question was, will this work if the model changes? So what I did is I added some code or some uh, script to my video or my worksheet that I made for the video, and I added this simulate modeling errors. So what I am doing is I am making calculations for my gain using the ideal formulas from above, and then I'm modifying them for my model. In other words, I'm assuming that I have a standard deviation of 10%, zero point 0.1, for each one of my gains. So they could vary with a standard deviation from my ideal, which is 10 hertz and a damping factor of 0.333 and 0.68. So going down here, if I hit a control F9, and I'm going to do it on this worksheet because this is a simpler one because it's only proportional errors. If I do an F9, you can see that the gains, the state space arrays, change every time I hit control F9, and that is due to the fact that I'm changing the open loop gains over here. So let me just hit control F9 again, and you can see that the gains are always changing, and they change with a standard deviation of 10%. Now, normally when I'm doing my system identification, I'm pretty good and I can get it within 2% most of the time, and in worst cases about 5%. So this is extreme. Also, I would like to say that if I was really testing this for real, what I would do is I would have this gain plus 10%, minus 10%, and this gain plus 10%, again, um, the 0.33, and then minus 10% of 0.33, and then this one at the current value plus or minus 10%. So altogether, that would be 27 values. And if I happen to have more parameters, you can, excuse me, you can see that the number of combinations I have to test for is can get to be quite large. But if I want to test this thoroughly with to say that I can get it within my system identification within 5%, I want to test with plus or minus 10%. Again, I would take this K value and then also use plus or minus 10%, the damping factor plus or minus 10%, and the natural frequency plus or minus 10%, and I wouldn't use this random method. Okay, so now that you can see that I'm changing the gains to simulate a modeling error or the open loop parameters, let's just take a look. This is the same graphs that I had before using the same parameters except for the deviation in the open loop parameters. And I'm going to hit an F9 and you're going to be able to see how it changes. Oh, let me also make this a little bit wider here. So you can see how the parameters get changing. Again, this is supposed to be 10, 0.333, and 62.28. So let's just keep on hitting F9 a few times to make you a believer. Now you see that time, you can see that the actual position fell behind by quite a bit, but again, the open loop gain has dropped by almost 30% from 10 down to 0.7, but still it gets into position. And I would never expect the gain to drop by that much, but I'm testing. And then you can also see the velocity and the acceleration down below here. So let's just do some more. Let me get this over. Okay, so you can see that this is really pretty robust. And if it's only changing by 2 to 5% in that range, you can see that it's almost dead nuts on. The only complaint I have about this method using all proportional only is there's no integrator to wind the actual position into the target position should there be a small error and the proportional gain is not enough to overcome the static friction. So now let me just show you another example. Now this is one of my normal simulations over here. And you can see I've got my uh, controller with a second derivative gain because that's what's required to place 4 poles. I got my hydraulic simulator. It's the same hydraulic simulator that was over here. So it's a linearized hydraulic model. And then I've got my definition of a closed loop transfer function. And I'm doing the substitutions and I get the characteristic equation in zeros up here. And if I, oops, too much. Again, I only need to match the coefficients for this is lambda to the 4th power to this. That's s to the 0 power, s to the 1st power, and I'm doing all the matching here, and I solve, and these are the controller gains in a symbolic form. So now using my ideal parameters, which is 10, again 1/3, and oh, I guess this time I use 20 hertz instead of 10 hertz, but that won't make any difference. Um, And then I calculate the gains. These are the gains that I would calculate assuming that I did a system identification with these parameters up here. And I've also calculated feed-forward gains, although I don't think they're used in this simulation. So now I simulate the model errors, again, the modeling errors, and I'm assuming that I have a standard deviation of 0.1, which again is very extreme. And you can see that here I have got this gain is varying from 10%, and it's the damping factor should be 1/3 or 0.333, and this should be 2 times this. What does that work out to be? Ah, natural frequency should be Uh, let's just calculate it out here so we know. W dot N. Oops. Okay, it's 125, 125.66. So you can see this has varied quite a bit. And now I'm doing step jumps, and I'm doing a simulation using Runge-Kutta. And so I'm using differential equations to do the simulation. I will just pause it here so you can see the math because I'm going quite fast. And what you need to do is pause the video to look at the equations because I don't want to take a lot of time explaining everything. But what I need to do is calculate out what the jerk is. I calculate out what the difference in the control output happens to be. Uh, this is the error between the target position and the actual position, target velocity, actual velocity, target acceleration, actual acceleration, target jerk, and actual jerk. And the Runge-Kutta integrates all that. And that's how I get my solution, which is this. And I have my time, position, velocity, acceleration, and jerk. And you can see that with the simulation, it gets into position quite nicely without overshooting, and I'll just hit a Control F9 a few times so you can see that. Oops, Control F9. Now this is making step jumps. I've got other simulations where we're not making step jumps. Takes it a while because this is a more complicated simulation. Okay, I've got another simulation here where I'm using Adam Bashford instead of Runge-Kutta, and this is a second order simulation, but it's basically the same thing, so I'm not going to go into it. I got a sine wave here, and let's just see how that works. So this is again uh, my I assumed that was 10. This is again 1/3, and this is 125.66. But we'll see what happens as I change the the errors or the open loop system to simulate modeling errors. And you can see it does a very good job. Again, that's the Adam Bash for it. This is a fifth order target or motion profile at like down here. And only I don't have the crosshairs on. So I'm going to do a Control F9 again. Oops, let me get down here so you can see the modeling errors. So you can see that the actual position and the target position are right on top of each other. You can see that it's very, very robust. And so placing the poles on the negative real axis, or attempting to, is a very robust way of tuning up your system. So I'm going to go down here and bypass all of this. This is the closed loop Bodhi plot. And let's see, let's go down here to the, okay, this is the PI Bodhi plot. Let's see, let's go down here, I minus PD Bodhi plot. And again, I can hit Control F9. And you can see it doesn't change all that much. You can see the parameters change down here. So now let's look at the zeros, the poles and zeros. Now ideally, all these poles will be on the negative real axis, but because there's errors, the poles are going to vary a little bit from where I really want them. But let's just see how robust this is. And the big thing is that you don't want the poles to go too far off the real axis, because that would mean it's going to oscillate. And you also want these zeros to be fairly close to the poles to kind of cancel them out. So in this case, these zeros kind of cancel out these poles, so you only have this one extra pole looking like a low pass filter. So going back up here, you can see that it doesn't change much. So let's go all the way up to the beginning here. And again, these are my calculations for the ideal calculations, assuming that my modeling is correct. And then I deviate the gain and the natural frequency and damping factor. So my gains that I use down below are going to be totally different from what the real or the model that's been modified happens to be, which is calculated up in the simulation part. This is my simulation using Runga-Kutta, where I update my state with position, velocity, acceleration, and my control output. I got my target generator here. This is my step generator, target generator. I've got many target generators that I use. And then I have to calculate out a jerk. Again, I calculate out the change in the control output based on my gains. And these are my errors here. And then I have to integrate it using the Runga-Kutta. And this is what I get. Okay, hopefully you can see that I test for robustness, and I don't do it in the traditional way of using like H infinity, which is great if you're using Kalman filters and you need to have something more robust than a Kalman filter. But most people are not using Kalman filters, and before I even had the math to even approach the ability to do Kalman filters, this is the way that I tested for robustness. And it's a much more basic way. It's obviously offline, but it works very, very well because my system identification is accurate enough where I know that I can just vary my parameters by plus or minus 10%, and I'll be and test them out. I know I'm going to be fine. Okay, that's the end of the video. Hope you like it. Bye.